than people who have, say, high serum selenium levels. So what Dr. Willett had was access to 4,480 blood specimens. If he wanted to, he could analyze all 4,480 of them, throw them out, assay them using some sort of a blood assay that measures serum selenium levels. Selenium is one of those trace elements that we have in our blood that's based on the diet that we eat. Certain leafy vegetables are high in serum selenium levels, and people might suspect that serum selenium levels, high levels, might give you different risks of developing cancer. So what Dr. Willett had was 4,480 previously collected blood specimens that were frozen from people who were in this hypertension detection and follow-up program. And as part of that hypertension detection and follow-up program, everybody was followed routinely to observe certain outcomes that happened to those people. And one of the outcomes that was recorded is whether those people developed cancer or not. So what Dr. Willett knew is 111 of these 4,480 people developed cancer after the hypertension detection and follow-up program had ended as part of this routine follow-up mechanism they had. He definitely wants to measure the blood levels of those 111 cases of cancer to find out whether they have high or low levels. But the question is, do you analyze everybody else? Well, if he did analyze everybody else, this is what his data would look like. He'd have 4,480 people. Once you measure their serum selenium levels, he could classify them as having low levels. Let's suppose N1 means the total number of people with low levels, or high levels, total number of people with high levels. Then he could also look at the list and see if those people with low levels or people with high levels would be on the list of the 111 people who developed cancer. He could fill in the A cell, fill in the B cell, fill in the C cell, fill in the D cell. He knew he had 111 cases of cancer. That's A plus B. Therefore, if he had 4,480 people to begin with, he'd have 4,369 people who did not develop cancer. D of them would be in the low-level selenium group, and D of them would be from the high-level selenium group. But if he analyzed all 4,480 people, he could fill in the numbers for A and B and C and D. He could calculate the risk ratio, divide A over N1, N1 being everybody with low levels, divide that by B divided by N0, N0 being the total number of people with high selenium levels. And that would be the value for that risk ratio from that cohort study using all 4,480 people. But again, mathematically, realize that that is A divided by B, in other words, among the people who developed cancer, the number of people who had low levels divided by the number of people who have high levels. That's the odds of having a low level among all the cancer patients. And then you divide that by N1 divided by N0, N1 being the total number of people in the original cohort with low levels, and N0 being the total number with high levels. But remember, to do this study, to fill in this table, he'd have to analyze all 4,480 specimens. And that might take time, and that might take money, and maybe the people who own these bloods might not have wanted Dr. Willett to use all 4,480 of them. Maybe they wanted to save some bloods for future studies. So what Dr. Willett did was the following. Only analyzed 210 of the non-cancer people, meaning, if I go back to the previous slide, he had 4,369 people from the original cohort who did not develop cancer. Instead of analyzing all 4,369, Dr. Willett decided to take a sample of 210 of them. So what Dr. Willett ended up doing is only analyzing the samples of the 111 cases of people who developed cancer and a sample, 210, of the people who didn't develop cancer. So he only analyzed 321 of the 4,480 blood samples. And as I mentioned, this type of study design might undergo a renaissance in the future years, is that lots of cohort studies now do exactly what the people in the hypertension detection and follow-up study did. They ask people to donate bloods, or they ask people to donate tissues, and they save those for future studies, like the one Dr. Willett was doing here, to allow people to analyze just a sample of those specimens to see if you could find an association between a risk factor, say serum selenium, that wasn't recorded back when the original hypertension and detection and follow-up study was done. So this is what Dr. Willett showed. Among the 111 people who were cases of cancer, 57 of them had low levels of selenium based on some threshold, and 54 of them had high levels. Comparing to that is the 210 people, the controls who did not develop cancer, only 84 of them had low levels. Only 126 had high levels. What Dr. Willett calculated was something called an odds ratio. Actually, it's an exposure odds ratio. He measured how common the exposure, low selenium, was among the 111 cases compared to how common it was among the 210 controls. He calculated the odds of having a low selenium level among the cases. 57 had low, 54 had high. 57 divided by 54 is measuring how common the exposure is among the cases. He did the same thing among the controls. 84 divided by 126 is measuring how common the exposure of low selenium is among the controls. When you divide the exposure odds among the cases by the exposure odds among the controls, you get something called an odds ratio, 1.6. Now the question is, what does that 1.6 represent? Well, remember, these 210 controls were chosen essentially at random from all the potential controls, all the potential 4,369 people who did not develop cancer. So his 210 controls is telling you approximately how common exposure is among. I'll give you an estimate of the relative size of B over D. So going back to Dr. Willett's example, and he measured his 210 controls and found that the odds of exposure among them was 84 divided by 126. He's getting an estimate of the odds of exposure among all 4,369 potential controls. So his 1.6, which is an odds ratio, approximately is an estimate of the odds of disease, odds of exposure among his cases, divided by the odds of exposure among all the people who didn't develop cancer in the original cohort. But remember, in the original cohort, which had over 4,000 people, only 110 of them developed cancer. So B divided by D is almost going to be the same as the relative size of everybody in the original cohort, N1 divided by N0. So his 1.6 is estimating the odds of exposure among the cases approximately compared to the odds of exposure among everybody in the cohort. Remember, that is the same as the risk ratio. So what Dr. Willett is able to do with only using 300 and some odd individuals from the original 4,000 plus people in the original cohort study is to get an estimate of what the risk ratio would have been in that cohort study if he analyzes the bloods of everybody in the study, all 4,000 plus individuals. So what the case control study became in this particular study is a very efficient way to obtain new information originally and to be able to get an estimate of what the risk ratio would be for that risk factor if he could obtain it on everyone. Now, why do I bring this up? I asked you all to think about, since last week, in the homework assignment, is thinking about doing a study to see if the island you lived on somehow was related to your risk of getting good or bad care for diabetes, and using data from a existing insurance database. And then as an add-on, I said, if you had a small budget to collect new information, what would you collect and on who would you collect it? And we'll get back to this case control design later today when I talk about that particular homework assignment, because I think it might be a good design to consider when you have existing cohort data, like the data from that homework assignment from that insurance data set. So let's hold the case control design in our memory until later today to give you as an add-on you might consider for certain cohort studies. So with that in mind, let me then move on to the last of our 4 study designs that I wanted to talk about, namely the experimental design. And let's go through a couple of examples of experimental designs and say a few words about them. First, a couple of